Today, I need to take a few moments to talk about the gravitational potential energy. So the title of today's lecture, I suppose, will be Gravitational Potential Energy, but the fact of the matter is, it'll only take me a few minutes to work that out because I already have a very good understanding of how potential energies are formulated. And so I'll do that. And then I have some applications of universal gravitation, specific, very essential problems to be solved. So I guess I'll say that everything that I'm going to do today is essential. So right off the bat, here we go. I want to talk about the gravitational potential energy. And you say, no need to do that because I've already studied energy. And I understand that there's gravitational potential energy associated with the location of an object in the gravitational field. And I know how to calculate it because it's mgh. All I have to do is select a position that I call 0, a certain height, and then measured from that height, from that 0 level, the height of objects, and I calculate mgh, and I know the quantity of gravitational potential energy. I also realize that what's really important is not where the reference level is, but the change in the gravitational potential energy. Because when gravitational potential energy changes, the law of conservation of energy indicates to me that I should find that energy somewhere else in the system. So don't worry about it, I already understand. Well, the trouble is, what I've realized now, and I did in the previous lecture, is that when I calculate the gravitational potential energy using mgh, there's a very significant assumption that I'm making there, and that assumption is that the acceleration due to gravity is uniform everywhere in space. That the acceleration due to gravity, where I start at 0 at a height here, and I raise something up to a final height, that the value of g is 9.8 meters per second squared at both locations. And of course, now I realize that that's not true. Last lecture, I derived an expression that says that just as the gravitational force diminishes as 1 over the square of the distance, so too does the gravitational acceleration. So as I go away from the surface of the Earth, the gravity gets weaker and weaker and weaker. And so the acceleration due to gravity is less and less and less. And in fact, in orbit, about 100 kilometers over the surface of the Earth, the gravitational acceleration drops off to about 8.5. Of course, the gravity in space is not 0, a very silly thing to say, because the satellites, like the International Space Station as an example, are in circular motion around the Earth under the influence of the gravitational force. So there is a gravitational acceleration there, but it is in fact weaker. So when I talk about the gravitational potential energy of planets, I need to consider the fact that the gravitational acceleration caused by the Earth is significantly different in space and varies according to 1 over the square of the distance. So I need a new form of the gravitational potential energy, but I know how to derive that because I have a relationship between the work done by a conservative force, and the force of gravity is a conservative force, according to all of the reasoning that we gave the first time we talked about gravitational potential energy. The work done by a conservative force is equal to the negative of the change of the potential energy. So all I have to do to calculate my new version of the gravitational potential energy is to calculate the work done by the gravitational force, and naturally the gravitational force I'll use for that calculation is the universal gravitational law given to us by Isaac Newton. So I'm just going to have to perform an integral here and then I'll have my answer. But there is a little bit of a detail. Just as when I'm solving a problem using gravitational potential energy as mgh, which I'll still do, by the way, if the changes in height are small, it's a good assumption that the acceleration due to gravity is g. I can still do that on small scales. This that I'm deriving is for large scales. So just when I'm solving those problems and I have to set a height to be 0, so too do I have to decide in this solution that I'm about to do, what is 0 gravitational potential energy? There's a convention for the choice of 0 gravitational potential energy that we all will follow. And so in a sense, the choice is less arbitrary. I will define, in this derivation that I'm about to do, that 0 gravitational potential energy is when two objects that mutually gravitate are separated by infinite distance. That is, two objects that are infinitely far apart have 0 gravitational potential energy. And we will always make that assumption that the potential energy at infinity is 0, is sometimes how they say that. That the potential energy is 0 at infinity. So now I'll proceed with this, that the negative of the change of the potential energy is going to be equal to, naturally, the integral of the force dotted into the displacement. This is my most general version of calculating the work, which must be equal to that potential energy. Now I'm going to specify this integral and then perform it all the way out here. So we take up a little bit of space as I do that. So this integral is going to be the integral of the force. Well, what force? The force that I'm talking about naturally is the universal gravitational force, which is G, the mass of one object, the mass of the second object, divided by the distance between them squared. That's the universal gravitational law. That's that universal gravitational force given to me by Newton. That force is a vector, naturally. That force is a vector, and that vector points radially. So I'm going to write an r hat in here, and the r hat naturally is a unit vector of 1 that points in the radial direction. Is a unit vector of 1 that points in the radial direction. R dot dr. I'm not going to change this into an integral of dx because it's a radial integral. Gravity is a radial phenomenon. So I'm going off a radius off that way from the origin of my coordinate system. It was our sort of arbitrarily chosen in the universe. Here it is, right? Where I put a mass, m1, and the other mass is at infinity, where the potential energy is 0. The other mass is at infinity, where the potential energy is 0. So I start with 0 potential energy. What I'm going to do is I'm going to have this mass m1 here and m2 off at infinity, and I'm going to bring m2 in from infinity to the vicinity of m1. I'm going to bring m2 from infinity to the vicinity of m1 so that I can define what is the gravitational potential energy between the two. As I do that, notice that the displacement vector, as I bring m2 from infinity inward, is toward the origin of my coordinate system, which is located at m1. And the r hat vector points to infinity. And so they point in opposite directions. The reason why I say that is that this dot product here that I do then will generate a negative sign. Will generate a negative sign. And so I'll write this as, having completed the dot product, the negative of the integral of g m1 m2 over r squared. I should have brought those constants out of the integral maybe. dr. It's no longer a vector integral. It's a scalar integral. And so that's the integral I need to compute, but those constants can come out of the integral so that it's negative g m1 m2, the integral of 1 over r squared dr. And as is typical, I find myself with an integral that's rather easy to do. I want to consider at this point the limits. What are the limits on my integration? Well, as I said, I start with m2 at infinity, infinitely far away, and then I bring it in to proximity with m1. So I'm starting at infinity, and I'm going to finish when the separation between the two particles, m1 and m2, is r, because I've chosen the origin of my coordinate system to be at m1. The position vector of m2 points from m1 to m2, and then that's r between them, right? So I bring it from infinity to a certain separation between the two. And those are the limits of my integration. Well, we all know that the integral of 1 over r squared is negative 1 over r. The integral of 1 over r squared is negative 1 over r. The negative generated by that integration is going to cancel this negative sign out in front so that g m1 m2 times 1 over r evaluated from infinity to r. So I have to evaluate those limits. That's final minus initial. So I'm going to make all of the math folks queasy by writing a thing that they would definitely disapprove of. So it's gm1m2, 1 over r minus 1 over infinity. Well, 1 over infinity is 0. 1 over infinity is 0. And they might imagine some greater mathematical argument to demonstrate that that's so, but I'm totally comfortable with just saying that 1 over infinity is a very small number indeed. So what I have as my result here on my right-hand side is that the work done by the gravitational force as I bring mass m2 from infinity to the proximity of m1 is equal to g m1 m2 over r. Notice it's now 1 over r dependence. Here's a problem that you might have psychologically. You need to get on board with this. It looks like universal gravitational force, doesn't it? But the r is not squared. They look the same. You have to be careful because I've had many students in the past who have a hard time squaring or not squaring and remembering if it's squared. Come on now, the gravitational force diminishes as 1 over the square of the distance because of that argument about the intensity of gravity being distributed over the surface area of a sphere that grows ever larger proportional to the square. So it's the gravitational force that's proportional to 1 over the square of the distance. This is 1 over r. So you're going to want to play heads up with that and make sure you're using the correct expression. But before I can call this completed, I have to consider the left-hand side of the equation because this is equal to the negative of the change in the potential energy. I have evaluated the work done by the gravitational force, and that is equal to the negative of the change of the gravitational potential energy. The negative of the change. So I have to write this rather explicitly. The negative of the change is going to be the negative of the final gravitational potential energy, which is the gravitational potential energy at r. That is the gravitational potential energy when mass m1 and m2 are separated by a distance r, minus the gravitational potential energy at infinity. And here is my reasoning for choosing the gravitational potential energy at infinite separation to be equal to 0. That is 0. And so the negative of ur minus u infinity is going to be the negative of the potential energy at r. And now I see an interesting feature of my gravitational potential energy. And here's my final result, because I'm going to solve for ur. The gravitational potential energy, which I will in the future probably write as u sub g, gravitational potential energy. I'm now writing as u sub r because of the notation in this derivation, but in the future I'd probably write as g, because what does that r mean? The gravitational potential energy at a separation r is going to be equal to negative g m1 m2 over r. That is my final result. Now, everything in the calculation is positive definite. The universal gravitational constant, certainly the masses, the distance between the two objects that are mutually gravitating is positive definite. This means that gravitational potential energy is always negative. Always negative. Gravitational potential energy is always negative, and this is the first time you're really encountering this idea. This is the first time you're really encountering this idea, but in all of physics and all of science and all of engineering, binding potentials, potential energies associated with attractive forces are always negative. By convention. That fact is caused because I chose the potential energy to be 0 at infinity. Gravitational potential energy is always negative. Always. It's an important fact. Now that I have that gravitational potential energy, I can write the total mechanical energy of planets in orbits, right, or satellites in orbit, and all these gravitational motions. I can write the total mechanical energy of the system as the kinetic energy, 1/2 mv squared, minus gmm over r, I almost said r squared, can you believe it? 1/2 mv squared minus gmm over r. And so I can write the total mechanical energy. So this is the new gravitational potential energy, and I might calculate the gravitational potential energy between objects, and certainly in your assignments you'll have occasion to calculate potential energies between two masses. And so that's it, a very, very simple description. Now what I want to do is shift gears a little bit and start making some practical, and that obviously is an essential calculation. I'd like you to be able to do that right off the top of your head to be able to demonstrate that, because to demonstrate that is to demonstrate understanding. So now what I want to do is just some practical application, essential practical applications of universal gravitation, because now we're going to want to use these laws that we have to solve problems of orbital dynamics, very exciting problems that we can solve because we're ambitious. We want to put a satellite in orbit, so we need to know how these things work. So what I'm going to do now with this extra space that I have, I'll just be of utility and use the board. I'm done with potential energy now. Over here, I'm going to do two practical applications of universal gravitation, and then I'll erase the board, and I think I have two more that I'll do after that. So let me consider, please, that the motion of satellites is very often nearly circular. For example, the motion of the moon around the Earth is very, very nearly circular. Of course, Kepler has told me that they are, in fact, ellipses. But you might make an argument and say, well, in approximation, let's say that it's circular because it's so nearly circular. Let's pretend that it's circular. We don't have to do that. We don't have to do that because It turns out, I'm not going to prove at this moment, I'm not going to prove, but it turns out that it's a lovely little mathematical observation that we can make, that the behavior of an elliptical orbit has many features exactly in common with a circular orbit whose radius is the average radius of the ellipse. As an object goes around in an elliptical orbit, naturally the radius changes, and it becomes its maximum value, the radius at aphelion, and its minimum value, the radius at perihelion, and it has an average value for that radius all the way around. In fact, you would not be surprised to learn it's the perihelion radius plus the aphelion radius divided by 2 is the average radius. I can make circular motion out of that and do my calculations with a circle of average radius and get the same answers for a lot of quantities. If I want to know specifically about the velocity at different locations in an elliptical orbit, that is when I'll rely on the conservation of angular momentum to get me those answers of specific velocities at specific points in an elliptical orbit. So I'm going to be doing calculations generally on average and talking about it as if it were circular. So consider some orbital motion, like the motion of the moon around the Earth. That is going to be circular motion, and I know from my studies of circular motion that the net force that acts radially in circular motion must be equal to the mass multiplied by the speed squared divided by the radius of the motion. That's a circular motion law, if you will. It's like a circular motion form of Newton's second law. Well, what is the force that is the cause of that motion? It's the whole point of this discussion. It is the universal gravitational force given to me by Newton. So I'm going to write Newton's gravitational force on this side, but I'm going to write it in a way that I mentioned before was a habit of notation of mine. See, I've written it as G lowercase m capital M over R squared. When I'm doing orbital mechanics, generally, there is, not always, but generally there's a situation where there's one object that is very massive that is being orbited by another object which is far less massive. That is not always the case, particularly, when I look up into the sky, about 50% of the stars that I see on the sky are not single points of light. They're actually two stars orbiting one the other. In that case, the masses are very similar to each other. Well, at least they're comparable. And then that's a slightly different thing. But very often it's a small mass and a large mass. And so I write it this way just as a convenience of notation that I just have to be careful about. Of course, I always have to be thoughtful when I'm doing calculations. So look what happens here. I have the mass of the orbiting object on both sides of my equation, which I can cancel. And I have an r on the left-hand side, which cancels one of the r's squared on the right-hand side, the left-hand side. And so I'll do a little bit of algebra here and solve for the velocity. And all I'm doing here is getting an equation that to me is an equation of great utility. It is the orbital speed equation. So I guess we can say orbital speed. I'll give it a name here. Orbital speed. It's often useful to calculate the orbital speed. This is the average orbital speed. In an elliptical orbit, the object will move fastest at perihelion and slowest at aphelion. Its velocity changes. So what I've calculated here is the average velocity of the orbit. And if the orbit is circular, or the average speed of the orbit. And if the orbit is circular, then this is the speed of the circular orbit. So that's a very useful thing to know, and that's an essential calculation, very quickly done. But it's useful to know. The next calculation I'm going to do is rather a surprising one. And I'm going to put a title on it right away. I'm going to call it, and essentially I'm giving away what's happening here. So maybe I just won't make a big deal out of it. Apparently I can't spell anymore. I'm going to do an intermediate calculation here. I'm going to do an intermediate calculation. Notice from above that I have an expression here that G times M divided by R is equal to the speed squared. That's what I just used for my algebra. So I'm going to take that intermediate step there and use it. The speed of an object as it goes around in circular motion on average is obviously going to be the circumference of the orbit divided by the time it takes to negotiate that circumference. So the circumference of the orbit being 2 pi r, this will be 2 pi r divided by the time period t, And I'm going to have to take that and square it, obviously, which will work out to be 4 pi squared r squared over the time period squared is equal to gm over r. A little bit of algebra applied to this, and I get a rather stunning result. Look what will happen. If I multiply this r over to the other side, I'll get an r cubed divided by a t squared. Reciprocating and flipping it to the other side, I know that we all know how to do algebra, so there's no reason for me to go through all of these algebraic machinations. But it becomes 4 pi squared over g times m, which is a stunning result, and I hope you've been paying careful enough attention that you see that and you go, whoops, there it is. Because one of the observations that Kepler had made about the orbits of the planets around the sun was that the time period of the planet's orbit squared divided by the average radius of the orbit cubed was equal to a constant. He knew that it was a constant value. He did not know what that constant value was. And now I find from Newton's universal gravitational law, which is where I began this calculation, that the constant is 4 pi squared divided by gm. And so we discover that Newton had discovered very much more than just the force law. Because consider, for example, do I know the time period of the Earth around the sun? Sure, it's a year. I know that. I can measure it. Do I know the radius of the Earth's orbit around the sun? That is, do I know the Earth-Sun distance? And you might furrow your brow at that and say, well, yeah, I know that we do, but how do we know? Just a little aside, radar, believe it or not. As we watch Mercury and Venus go around the sun, we can send radar signals out into space that bounce off those planets and return. Based on the time to go and return, we can measure the distance. We can also measure the angle as they're on one side of the sun and the other side of the sun. Draw some triangles, and from those triangles surmise the Earth-Sun distance. So the radius of the Earth's orbit around the sun, on average, is known. Therefore, the only unknown quantity in this equation is the mass of the object that is being orbited, the mass of the sun. This is how we know. This is how we know the mass of the sun. This is how it's determined, according to the gravitational interaction between the sun and the Earth. It's really quite spectacular. It also means that I can determine the mass of any other objects that I see mutually gravitating each other. For example, if I observe the motion of a moon of Jupiter around Jupiter, I can measure the radius of that orbit by making astronomical observations, and I can measure the time period of the orbit simply by timing it as I make my astronomical observations, and I can determine the mass of Jupiter. I can determine the mass of all of the planets and make astronomical observations. So it's quite a spectacular result that's of really, really tremendous utility when I'm calculating things, so worth knowing. Now, to do something else practical, what I'd like to do is have a look at how the gravitational potential energy will work, total mechanical energy. So the total mechanical energy of any physical system, any mechanical system at any rate, is the kinetic energy plus the potential energy. But now I know what that potential energy is equal to. The kinetic energy, 1/2 mv squared minus, because the gravitational potential energy is always negative, minus g mm over r. And that is the total mechanical energy of the system. But I want to make an observation about this and take it in another direction according to an essential that I just did. Recall that I discovered that the square of the speed is equal to gm over r. The square of the speed is equal to gm over r. That's what I just did in the previous essential. It's the orbital speed equation squared on both sides, and that's what I get. So I'll make that substitution here into the total mechanical energy, and what I get is 1/2 of the mass multiplied by the speed squared, which is g, m, the mass of the object being orbited, divided by r, minus g, m, m, divided by r. So just cleaning this up a little bit so I see what I have, 1/2 g, m, m, and all I'm doing is moving this little mass around. I'm actually wasting my time a little bit here. m, m over r, like that. Well, that's easy enough to calculate, and I find that the total mechanical energy of the system, the total mechanical energy of the system is 1/2 gmm over r minus gmm over r, which is obviously going to be negative 1/2 gmm over r. But gmm over r is the negative of the gravitational potential energy. Gmm over r is the negative of the gravitational potential energy. Remember, the gravitational potential energy is always negative. And so GMM over R is the negative of the gravitational potential energy. And so what I have here is a realization, a useful calculation, that the total mechanical energy of an orbital motion, that the total mechanical energy of that motion is equal to the average gravitational potential energy divided by 2. Notice that I put those little brackets on the gravitational potential energy. I put them there to indicate that what I'm talking about is the average gravitational potential energy. That is, I'm talking about the gravitational potential energy calculated according to the average radius of the orbit. I'm still doing that trick where I treat an ellipse as if it's a circle. So the average gravitational potential energy divided by 2 is equal to the total energy of the orbit. That is a very practical equation. If I want to do the total mechanical energy, sure, I can add the kinetic energy and the potential energy together and calculate it that way. But I might find myself in a problem-solving situation where I know the average gravitational potential energy. Just appreciate that half that energy is the total mechanical energy of the orbit. By the way, if the gravitational potential energy on average is negative, this means that the total mechanical energy will be negative, because when I divide by 2, it's going to stay negative. And that's true. The total mechanical energy of an orbit, the total mechanical energy, is always negative. This is what we call a bound state. The energy of bound states in our science is always negative. If these two have a total mechanical energy, that these two objects, whatever they are, if they have a total mechanical energy that becomes positive, then they are liberated from one another. They are no longer bound. Binding energy is negative. Binding energy is negative. So I sometimes call this, I have a tendency to call this the mean value for physics reasons further along. Call that the mean value. But yeah, whatever you want to call it Susan, if you like. One more thing, because once I understand this gravity and I think about orbits, I might plan myself a trip to Mars. And in doing so, the very first issue that I have is I got to get off the surface of the Earth. And so what I'd like to do is calculate what velocity I have to have at takeoff so that I can escape the Earth. This is naturally referred to as the escape velocity. I need the escape velocity, so write this. Just put a label on it. Escape velocity. The escape velocity from a planet, all I have to do is consider that, as I just mentioned, the binding energy of a system is negative. In order to escape from the system, what I need is the total mechanical energy to be such that when I arrive at infinity, rather absurd statement, but when I arrive at infinity, I have a kinetic energy of 0. Boop, here I am. I have escaped. That's the minimum for escape. It's the amount of energy required to escape to infinity. Oh, I'm not going to infinity. I'm just going to Mars. Well, yeah, then it takes a little less energy. It takes a little less energy. But to truly escape, I need to get all the way to infinity, which means my total mechanical energy, E, which is equal to 1/2 mv squared, minus G, the mass of my spaceship and me all together, and the mass of the planet, like Earth, for example, divided by R. That has to be equal to 0. Because if you have a negative total mechanical energy, you are bound. If you have a positive mechanical energy, then you are free. And so 0 is the critical point. So now I'm going to stir this equation around and solve for the velocity. Is quite simple. You'll see what will happen. The masses will cancel. A factor of 2 will go to the other side. And what I find is that the escape velocity is equal to the square root of 2. Not the way traditionally we write that. The square root of 2gm over r. So what I've accomplished today in the lecture, besides just defining the universal gravitational potential energy, is that I've done a couple of very, very practical examples that can be applied to solving orbital mechanical problems. These 4 or 5 equations that I've come up with, combined with my realization that the angular momentum of orbits is conserved, makes it possible for me to solve a very, very sophisticated and very interesting number of practical problems of orbital mechanics.